This video will cover some best practices for your data science workflow when dealing with relational data. By the end of this video, you should understand why it's important to check if data exhibit referential integrity, how you can check to see if data exhibit referential integrity, and how R performs joins if neither table contains a unique identifier. The R code used in this video is available on the Learning Management System. You'll need the data files customers2.rds and orders2.rds. You should download those now if you'd like to follow along. Referential integrity is an important concept in relational data. In fact, properly performing joins on relational data requires referential integrity. As we saw in previous videos, referential integrity requires that primary keys are unique and that each value of a foreign key has a corresponding value of the primary key in a different table. Relational database software ensures that these facts are true. R does not, and so if you want to check for referential integrity, you might have to do a little bit of extra work. In your data exploration process, you'll want to understand if relational data you have exhibit referential integrity, and so there are some checks you should perform. First, you should identify primary and foreign keys in each of your tables. After you do that, you should determine if primary keys are unique within their tables, and then if each value of a foreign key has a corresponding primary key. So how can we do this in R? You can use dplyr commands to check to see if primary keys are unique by looking for duplicated values of the primary key. As an example of one of many possible methods for doing this, you could take the data in the table that contains the primary key. You could use group by on the relationship variables, then use the summarize verb and count the number of observations within each group using the n function. After that, you would filter to the number of cases where the observation count is greater than 1. Referential integrity requires that the primary key uniquely identify observations. Therefore, the observation count should be 1 for each combination of the primary key variables. And so this should return 0 records if your primary key uniquely identifies each observation. Let's look at this in R. First, I'll run some setup code, including loading a couple of data files. Customers2.rds I will store in the customers table, and orders2.rds I will store in the orders table. I'll run that code now. These are different from data we've seen in the past, so it's important to take a look at them. First, I'll glimpse both of the tables. You can see these are variables that we're familiar with. The customers table contains a customer ID, the name of the customer, and the planet they're from. The orders table contains the product name, the customer ID, quantity of product that they've purchased, and the price. Printing out the customers table, we can see where the difference from previous data are. Importantly, the customers table no longer exhibits unique values of the customer ID for each customer. Customer ID 7 is duplicated, first for the customer Han Solo, and then for the customer Han Duo. Looking at the orders table, you can see it's very much as it was before, but also note that customer ID 7 has purchased 2 items. I've introduced these errors into these tables so we can investigate how you might determine if your data exhibit referential integrity. Going back to my code, the first thing that we would like to do is check whether or not the primary keys uniquely identify observations. The customers table contains a primary key, customer ID. What we're going to do to check for unique values is to take the customer's data. I'm then going to group by the primary key, which is customer ID. I'll then pipe that to the summarize verb. I'll count the number of observations within each group, each specific value of customer ID. I'm then going to filter down to cases where the number of observations is greater than 1. If there's more than 1 observation for a given customer ID, it doesn't uniquely identify observations, and it fails to check that it would be a primary key. So let's run that code and look at the output. And you can see in the output data, customer ID 7 has a count of 2 observations. There are 2 cases of the customer ID 7 in that table, so it fails the check of being a primary key. Referential integrity also requires that each value of foreign key has a corresponding value of the primary key in the table where it's the primary key. Again, there are many possible ways to investigate this. One would be to use an anti-join. You'll take the foreign key table as the left table. You'll anti-join it to the primary key table as the right table. And this is going to return observations from that left table where the foreign key does not occur in the primary key table. Referential integrity would require that this check return 0 observations. Let's perform this check in R using our sample data. So here I'm just going to take the orders table. I'm going to pipe it to anti-join using the customers table as the right table. I'll run that code and look at the output. You can see, looking at my output, that customer ID 18 is returned, which means customer ID 18 occurs in the orders table, but does not occur in the customers table. This violates referential integrity because we have no customer information for customer ID 18. You're often going to encounter real-world data that you would like to join, but the data come from different sources. When data come from different sources, there's no guarantees of referential integrity. So before performing any joins in your data, you should determine, first, what are the relationship variables? Second, do you expect a relationship variable to be unique? Do you think it's a primary key? And then investigating, does the data match your expectations? Are primary keys unique? And do foreign keys have values that are always represented by primary keys? These checks for referential integrity are a critical part of your data exploration process. Joins won't behave the way you expect them to if you don't have referential integrity, so it's good to investigate these things before you start joining data. Often, data from multiple sources are not going to exhibit referential integrity. For example, if you're joining data by date, the date ranges may not fully overlap. One data set may be missing some observations. Again, if you're thinking about data where you're joining by date, there may be a date range that's missing from one data set, but not from the other. Additionally, data sets might not use precisely the same values for relationship variables. For example, one data set could use Washington, D period C period to represent Washington, D.C., and the other could use Washington space D.C. with no commas or periods. Relationship variables have to be exactly identical. These pieces of text aren't, and that would cause your join to fail on those observations. Some of the issues here, for example, date ranges that don't overlap, you should simply just be aware of. But other issues, for example, Washington, D.C. not matching the corresponding text in another table, might require additional data wrangling. When dealing with real-world data, you may sometimes want to join data where there is no primary key in either table. This means that combinations of the relationship variables are not unique in either table. As an example, suppose I have two tables of data. One of the tables is courses taken by all students in each semester. So I have a listing of students and a listing of courses they've taken. Each student can take multiple courses, so the student is not unique in this table, nor is the course number. And then second, I have a table of courses taught by professors in each semester. Professors teach multiple courses, but also a given course might have multiple professors. Suppose I want to join these two tables on course number. In that case, there's no unique combination of relationship variables, and that will lead to a different type of join than you might expect. So how do R and other relational data systems deal with joins where there aren't unique combinations of relationship variables? What they're going to do is create an output table with every pairwise combination that they can form of relationship variables between the two tables. You should be aware that this can vastly increase the number of observations in your output table. So before you do this, you need to think about whether it's what you want. This type of join, where R is attempting to form every possible pairwise combination, is called a Cartesian join. Just as an example, if your left table has 12 observations, where the relationship variable month is equal to 1, and your right table has 12 observations, where the relationship variable month is equal to 1, the output table would have 144 observations, where month is equal to 1. It would form every pairwise combination of each of those observations. Let's look at this as an example. So suppose I have these two tables of data. The first table has an ID column. The ID values are 1, 1, and 2. And the second column is LTR to represent letter, where the letter is A, B, C, or D. The second table, again, has an ID column with values 1, 1, 2, and 2. And then the sim column has symbols in it, the @ sign, the hashtag, the $sign, and the %sign. Suppose I was to perform a natural join in these tables. The ID variable would be the relationship variable. What is R going to do? It's going to create an output table that has the ID column, the letter column, and the sim column. It will look at the first table, see that the relationship variable ID is equal to 1. The corresponding letter is A. It will then look in the second table, find every occurrence where the ID variable is 1, and form a corresponding observation with that symbol. So we have 1A and the @ sign, followed by 1A and the hashtag. It would then move on to the second observation in the first table. Again, the ID is 1. This time the letter is B. It would look at the second table, look for every occurrence where the ID variable is equal to 1. And again, it would form observations 1B and the @ sign, then 1B and the hashtag. Then it would look at the third observation in the first table. Again, the ID is 1. This time the letter is C. And it once again forms two observations, 1C, the @ sign, 1C, and the hashtag. Finally, it would move on to the last observation in the first table. The ID here is 2. It would match that to observations with ID value 2 in the second table. So you get 2D and the $sign, then 2D and the %sign. There are no additional values of the ID variable in the second table. So regardless of the join type, this is where the join would end. So you can see here, even though the first table only had 4 observations and the second table only had 4 observations, because there were repeated values of the relationship variables in both tables, the Cartesian join resulted in an output table of 8 observations. This lets you know that you should be cautious when you're joining data from multiple tables where the relationships don't form unique combinations for each observation. Just to look at an example in R, remember, in the customers table, there were repeated values of the customer ID number 7, and likewise, in the orders table, there were 2 orders by customer ID 7. Let's perform an inner join on these 2 tables to see what we get. Looking at the output, you can see that orders for customer number 7 have been duplicated. Row 3 and row 5 use the exact same order information, as do row 4 and row 6. Row 3 and 4 use the first iteration of customer 7, and row 5 and 6 use the second iteration of customer 7. Again, this might not be what you were expecting if you were joining these 2 tables, so it's important to check for referential integrity before you attempt to join your data.